All right, let's get started. Welcome to the session on lazy evaluations. My name is Venkat Subramaniam. We're going to talk about this wonderful feature of evaluating things as and when it's needed, as and when it's on demand. So we'll talk a little bit about what's lazy evaluation, and then we'll talk about some of the ways we can actually apply it. So what does it really mean to be lazy? Well, in life, being lazy means we don't get any work done. Well, there's a difference between procrastination and being lazy. Well, procrastination is when we haven't done what we are supposed to do. Laziness, in this case, is we are going to wait until the last responsible moment to actually evaluate. The reason for this is, as we are looking at technologies, the applications of computers, we are facing a very high demand on computing resources. And we can't really get more efficient by trying to run things faster, but instead what we try to do is to get more efficient by postponing operations and only doing them on demand, and in the process, get an opportunity not to do certain things that shouldn't be done in the first place. So in other words, laziness can directly relate to efficiency of code, and that's one of the reasons why we really want to aim for laziness. Well, laziness is not very common in imperative style of programming, but in functional style of programming, we use laziness very often. So this is extremely common in languages that are functional programming languages. Well, with most mainstream languages today beginning to support functional style of programming, we can certainly do laziness in those languages as well, and we'll take a look at some of those examples. But before that, I want to talk a little bit about just the way computing actually works, the way that we are used to, but what are the options available. One such thing is called the applicative order versus normal order. Let's just examine that just a little bit to get a feel for what that actually means. Let's say for a minute we have a function, let's say we have a function called add over here, and that's going to simply take two parameters, let's say parameter 1 and parameter 2, and all that it's doing is something extremely simple. It's going to return the sum of these two operations. Let's also say for a minute I have another function, we'll just call it as evaluate, that takes a value in and it simply returns the value. That's all it's doing. So pretty simple code, as you can see, nothing really exciting. But I want to come down here and I want to go ahead and call this particular method evaluate. And of course, once I call the evaluate method, I want to say to this I want to pass the add method with 1 and 2. So obviously in this case, when I run this code, it's going to produce a result of the add and display it. Now clearly in this case, if I were to just go ahead and put add called, just for us to take a look at and see this being called, sure enough, add was called. Now if you go to any programmer and ask them, when is add being called? Well, we'll kind of laugh a little bit and say, don't you know this? This is obvious. Add is going to be called first, and the result of add is going to be passed to evaluate. Well, that's called applicative order. Applicative order is what almost everybody in this room, including me, uses all the time. But it doesn't have to be that way. Just to entertain this thought, let's look at this a little bit different. I'm going to go ahead and write the code here. I have add A and B equals A plus B. This is simply a little bit of a Haskell code. And I'm going to say evaluate, and I'm going to say value. I'm going to return the value. And I'm going to say, in this case, print. And I'm going to call the evaluate, call add 1 and 2. And clearly, in this case, it produces a result of 3. So pretty much equivalent code to what we saw in Java. Here's the Haskell code. However, there are a few interesting things happening here in Haskell. Well, this is line number 1. I'm at character number 16. So let me get over here to the command prompt. I have the REPL running here for Haskell. And I'm going to load this particular file, which is the sample.hs. I'm going to put a breakpoint on line number 1, character 16. And I'm going to invoke the main function, as you can see right here. And sure enough, you can see it hit the breakpoint, and it's waiting right there saying, hey, I'm waiting to run further. So clearly, add has been called, and you can see that the breakpoint is on line number 1, characters 11 to 15, it's waiting there. Now, of course, if I ask it to continue, you can see that it finished the job. Great. So it seems like it was similar to what we saw in Java, but with a certain difference. In the case of Haskell, though, the order in which it evaluates method calls is called a normal order. I really laugh when I hear the word normal order because it seems it's really abnormal. We don't actually use this quite often. So very few languages actually do this, and Haskell is one such language. Normal order simply means it is not going to evaluate when you apply it. It's going to evaluate only when the value is actually needed. So if you closely look at this code looks very similar to the code here in Java, not a whole lot of difference as you can see, at least visually. However, if you look at the code, Haskell says, well, I'm going to call add 1 and 2, add with 1, 2, and Haskell says, yeah, I'll come back and do it later, no rush about it. Well, I want to call evaluate. Yeah, I'll come back to it later, no rush. I want to print the result. It says, okay, now I better get my work done. So it actually postpones it until you actually begin to use the result. As a result, if you notice here, if I go back and return a 42, when I run the code, of course, it displayed 42. However, Haskell says, hey, go ahead and call add with 1 and 2, and Haskell says, yeah, I'll get to it eventually. Hey, go ahead and call evaluate. I'll get to that eventually. Well, go ahead and print the result. Okay, let me call evaluate. Evaluate says, whatever you give me, I don't care, return 42. And Haskell says, gosh, I don't have to evaluate that stupid call to add and can completely bypass it. That's normal order. So going back to the example again, if I load sample.hs one more time, if I put a breakpoint on line number 1 and 16, much like what I did a few minutes ago, but now I call the main function, notice it never hit the breakpoint. And the reason it did not hit the breakpoint is it never ever had to call the add function because add is being lazily evaluated. It's a normal order. So we can see already how the languages can become intelligent by completely postponing evaluating a function until the result of that function is actually needed. And if you never ever care to use the result, it saves all the time. Imagine for a minute that add is not such a very simple function, but imagine add is going to take a lot of computational complexity to implement. Well, what's going to happen if that's a very complex method that's going to take time to run? Well, sure, you are better off not running it until you know for sure that result is needed. So you are going to be more efficient with this code because you're very smart about not running it when you don't need it and only running it when it's necessary. So you automatically get efficiency in that regard. But it turns out, unfortunately, some languages are born lazy. Whereas other languages, you have to really work very hard to be lazy. Those languages are kind of like me, right? Sometimes my wife would come to me and say, why don't you just sit down and relax? I would say, how do you do that, right? So some of us are wired that way. We cannot just relax. We got to be doing something or the other. Well, it takes a lot of effort to be lazy in these languages. Well, languages like Haskell, laziness is the norm. Laziness is the default behavior. Whereas in languages like Java, and to a certain extent language like Scala, we have to put a little bit more effort to be lazy. But let's entertain this thought just a little bit to see how we can extend this thought a little further. I'm going to write a little code here in Scala to just examine this, and then we'll come back to Java after this. So let's say for a minute I have a function called compute, and let's say this is taking some value input, and I'm going to simply say, in this case, this particular function is going to return, let's say, input times 2, very simple computation, but I'm going to go ahead and put a little print statement that says compute called, let's say. Now, in this particular case, generally speaking, printing these things doesn't make any sense because you want these functions to be pure, but I'm just using them as an example to show that these methods are being called, but obviously we didn't do these things in the production code. So what I'm going to do here is I'm going to say a value, oh, let's go ahead and call it some value x equals 5, and I'm going to say if x is greater than 5, let's say it is 2 to be very clear, and then I'm going to say and compute, oh, let's go ahead and say some value 5 here. I'm going to simply print, let's say this is going to be is greater than 5 also. I'm going to print result, and I'm going to then say else, let's simply say no result. Well, if you look at this very simple example here, obviously the value that I've started out with here, which is x, is going to be a value 2, and as a result, it's not going to be greater than 5. So what's the consequence of this? Well, when I run this little code, you can see no result got printed, but obviously it never got to this particular call. Now we call this as short-circuiting in programming. Well, almost every single programmer you know should be very comfortable with short-circuiting. That's one of the things we learned quite early on when it comes to programming. We know that if the first expression turns out to be a false, then the remainder of the expressions in the AND will not be evaluated. We program knowing that pretty well. However, here is one of the questions to think about. Well, this is great that because 5 is not greater than, x is not greater than 5, it never evaluated the compute. That's great. But what if I were calling the compute more than once? Wouldn't it make sense to say temp equals greater than 5 and val temp equals compute after all? Now, if you look at this code, the question you should ask is, will compute be called or not? What do you think? Will it be called? Everybody raises the hand. Let me rephrase the question. Should it be called? No, because you know it should be lazy, right? Now here is when you're going to say, I wish it was this, but it's not. How sad that is, right? So what do you think Haskell will do in this case? Will Haskell call it or not? It will not, right? Haskell will be lazy about this because Haskell is going to say, oh, you never use temp, so I'm going to save that effort and it would never call it. Whereas, what is Scala going to do? Well, let's go ahead and run this code, and that's pretty sad, isn't it? It did call that, even though we're not using the result. After all, in this case, Scala was not lazy. Well, thankfully, though we don't have to work really hard, we could say lazy val, and we can get back to the same thing in Scala as well. You have to just work a little extra to say, hey, could you be lazy today, please? So the definition of lazy here versus not putting it there, you can see compute was called. If I declare lazy over there, you can see that never got really called. So that is something you could potentially do, is to employ laziness. Now we got to be very careful using laziness, of course, in languages that support imperative style of programming, because if the code had a side effect, we cannot be lazy about it. Because the minute a code has a side effect, it has either a print, a logging, or writing to a database, sending some messages to a remote system, whatever that could be, then you cannot be lazy, because when an execution of a code is known outside other than the final result it produces, we definitely cannot be lazy in those cases. So that's one of the reasons why language like Haskell provides laziness by default, because the language from the get-go provides pure functions, and you have to use special syntax to create impure functions. Language like Java and Scala and several other languages, the default is impurity, and you have to work really hard to create pure functions, and that's one of the reasons why laziness is not the default in these languages. But wouldn't this be nice to do in a language like Java as well? When the answer is, we can. So in Java, we can get laziness using Lambda expressions. So Lambda expressions give us the way for us to introduce laziness. Now, how so? Well, the reason for that is if you give a Lambda expression, the Lambda expression is not going to be evaluated until you specifically call the particular Lambda expression. So you can defer the execution of Lambda expressions quite effectively, and so you can introduce laziness. So let's entertain this thought for a second here and see how that's going to work. Let's say we have a compute method, much like we did a few minutes ago, and I'm going to have an input coming in, and I'm going to simply say compute called right here, and this is simply going to return, let's say, input times 2. And of course, what I'm going to do here in the case of Java is I'm going to say, let's say, int x equals 2, and much like what we did if x is greater than 5 and compute of, let's say, the value, in this case, let's say 5, is greater than 5, let's say, oh, in this case, I'm going to simply output a result, much like what I did on the other side. And else, I will simply say else, we will simply say no result. So given this, I want to try to bring back the laziness into this code. Let's see how we can do this. So when I run this little example, you can see the compute was not evaluated. Now, on the same token, if I were to create a temp over here and put this back here, of course, you can see that it really ended up calling it. But how do I really make this lazy? Wouldn't it be so cool if you can just say lazy here and be done with it? Sorry, that doesn't work. So what can we do? Well, it turns out it is not really that bad. We can actually end up doing something very similar to this. So to entertain the thought, let's go ahead and create our little example here. We'll create a class called lazy. So my class lazy is going to provide me a little bit of a laziness here, if you will. And I'm going to first of all say optional of t. And I'm going to specify this is going to be the instance or the value that I want to store. So I'm going to bring in the optional in this case. Now that's going to be a little private field I have stored right here. Let's also go ahead and create a little value here, which is of type, and we'll call it get. But what am I going to do here within the get? Well, within the get, what I'll do is I'll say if value dot is present, and I can ask him if the value is actually present. If the value is not present, I can say value equals optional dot off, and then we will call a supplier, and then we'll call a get on it. We'll come back to what that is in just a few minutes. And then, of course, once we do it, I simply return value dot get and return the value. So if you notice what I just did here, in the get method, I go to this optional and say, hey, optional, what do you have? And I'm going to say optional.empty to begin with. So I've initialized the optional to empty. Essentially, it doesn't have a value in the beginning. And in the get method, I'm saying, if it is present, well, if it is not present, then go ahead and create the value for me. And I'm using a supplier, which we'll see in a minute, and then assign it to the value. And then, of course, just return the value that you have stored at this point. Well, that leaves us the supplier, so we will say supplier, and in this case, I'm going to say supplier of t, and that's going to be the supplier we're going to bring in. Well, the supplier is a functional interface, so I'm going to bring in the function right here, so that brings us the function supplier. So what is a supplier? A supplier is a functional interface with one method, which is the get method that I've used right there. Now, there are a few interesting functional interfaces in Java 8. One of them probably you've seen quite often is the consumer. Now, what does the consumer do? Consumer swallows everything, never gives you back anything. It's one of the most evil interfaces in my opinion, right? So it just takes away stuff, doesn't give you anything back. Well, predicate will take an input and give you a Boolean. On the other hand, if you look at a function interface, it'll take an input and return an output. But my favorite interface is the supplier interface, because supplier never takes anything, but it always gives you something. So I call this the mother's love kind of interface, right? It doesn't have any expectations, but it keeps on giving to you. So that's an example of what a supplier can do, just return the value back to you. But of course, I need a supplier. Where do I get the supplier from? So I'm going to go ahead and write the constructor for this particular class where I say supplier, and I'm going to say the supplier, and I will simply store away the supplier given to us in this particular context. So all I have done is create this lazy. So now notice what I'm going to do here. I simply replace this with lazy of integer temp equals compute, and of course that's going to be a supplier, so I turned it into a Lambda expression. So all I did was something very similar to what we did in Java, but we wrote ourselves a lazy in this particular case. You can tuck it away into a library and reuse it in your code if you want to. So all that the lazy is doing in this case is saying, I'll give you the value, but only when you ask for it, not ahead of time. So now I can simply say .get over here and invoke that particular call to this particular function very easily. Of course, in this case, it's going to be lazy of integer, and I'm going to specify that it's going to be holding on to this particular Lambda expression. So let's wrap that into the Lambda, and you can see that's actually doing the job right there. So even though we created a temp ahead of time, the value of the temp is not being initialized until a later time when we actually ask for it. Now, of course, in this case, you can call get any number of times, but the first time you call it, it will initialize the variable, and every other time it will simply return back the value it has stored, and as a result, we're not recreating the value over and over. That's one benefit you get out of this. So the moral of the story here is, in most languages that support Lambda expression, even if the language doesn't support laziness directly, we can have laziness using Lambda expressions. And the reason is the Lambda expression is not evaluated until you actually call it. So in this case, if you notice, we created the Lambda expression right here in on line number 28, but it is actually invoked only when the get is called, and as a result, when the supplier.get is called. So the Lambda evaluation is postponed until the time you actually come in to call the get. But what if you never call the get on the supplier? Well, the Lambda will never be evaluated, and as a result, that object will never be created. So you can postpone creating objects until on demand, and so any expenses you would incur in creating that object is removed and is only given to you only on demand, and that's the benefit you get out of this. But the laziness actually goes a lot further than just using it this way. And one place where we're going to see this quite extensively in Java is in the Streams API. So the Streams API fundamentally is, by default, is lazy in the case of Java. It doesn't evaluate things until it is on demand. So if you look at the Stream API contains two kinds of functions. Those are called intermediate operations and terminal operations. Intermediate operation is an operation that yields back a stream. So here is a very easy way to know whether a function on a stream is an intermediate operation or a terminal operation. Quickly take a look at the return type of this function. If the method is returning a stream, then it is an intermediate operation. If it is returning something other than a stream, then usually it's a terminal operation. So intermediate operations don't do any work until they really are invoked finally by a terminal operation. So you can have laziness built in very effectively in the code right off the bat. So let's take a look at an example of how we can be lazy with stream evaluation. How can we bring in some of the laziness into this? Well, let's take a look at one example of this right here. If I really wanted to perform a certain computation, I can start using the Streams API. So let's go ahead and bring in the stream here. And what I'm going to do in this particular example is, let's start with a list of numbers for a minute. So I'm going to say list of numbers 1 to 10, and I want to go through this list and let's say return the double of the, let's say, of the first even number, let's say greater than 3. And I'm going to change this list just a little bit to say 5 and 4. So if you look at this code, we are saying return the double of the first even number greater than 3. So notice the code I can use with the streams in this particular case. I can say numbers.stream. And so think of a stream as a very fancy iterator. But the minute you see the word stream, immediately the word lazy should come to your mind, because stream fundamentally is lazy. If we don't know that stream is lazy, we are in for some surprises because the methods may not be called when we think it is being called. So it's important to get comfortable with the laziness of streams real quickly. Now I'm going to say filter. In this case, I'm going to say given an element, I want elements greater than 3. Filter again, given an element, I want only the even values. And then I'm going to say map over here, given an element, double the element for me, and then find the first element out of that. So that is the code we just wrote. to produce that result of optional 8 to say that sometimes the result may or may not exist, and that's basically what it's returning to us. But if you look at this code, this is a very concise code, but when you look at this, a fear may go through in your mind to say, oh my gosh, looks like we did a lot of extra work. What a waste. If we do all that work and we only pick the first result, that would be really a huge amount of waste. Especially if this collection were very large. What if you had 1,000 elements or 10,000 elements in this collection? What a waste to go through all the processing and then throw that all away and take the first value. Well, surely that would be really unfortunate if that were the case. But fortunately, though, streams are fundamentally lazy, and as a result, we are not going to incur any more expense evaluating this than absolutely necessary. Fundamentally, it is lazy. So let's take a look at how this is fundamentally lazy. So to understand that, let's go through the sequence of what this is actually going to do. Well, the very first thing here is, it is going to evaluate that particular function on the value 1, and because 1 doesn't really pass that particular computation, it simply throws away and shifts over to 2, and so for 3 until it gets to 5. When 5 enters this function, it'll pass through that particular predicate, get to the next filter, and 5 will fail this particular filter because 5 is not even. Then you take 4 and you apply the first filter, that's passed, then the second, then the third, the map goes through, and the find first says, look, I found the value and I'm done, and it would never evaluate any value past the value it hit, and the reason for that is absolutely lazy. In other words, if the computation was eager, what would it do? It would first apply the first filter on all the elements first, arrive at a resulting collection, then eagerly evaluate the next filter, then do the map, and eager evaluation will simply suck, because it would have done all that extra effort only to throw away most of the result and get the first value. But because this is lazy, it is going to evaluate in a completely different order, but only enough to get you the result and no more. So to understand this, let's take a look at an example here. Just take a look at this map for a minute, and let's see what it's doing. Well, I'm doubling the value, so I'll say sample double it for a minute. And I'm going to say, in this case, double it takes a number, and it simply says return number times 2. And you can see in this case, of course, it's going to run through this particular double it function and provide the result for us. But I'm going to introduce quickly a little output here that says double it called with, and let's simply say number. Once again, I want to remind you, it's not a good idea to put side effects in these functions, so you would never ever do this in real code. This is just a demo. I want to show you that it actually is calling that function. A better way probably would have been to put a breakpoint and then show that it actually hits the breakpoint. Now, when I run this code, you can see it called the double it only for 4 and definitely not for any of the other values. It never ever called it for 6, 8, or 10, even though 6, 8, and 10 are greater than 3 and are even. If you extend this a little further to take a look at this particular function right here, what is this doing? Well, this is obviously checking if the value is even. So I'm going to say sample is even, and let's go ahead and write the function over here, which is a Boolean, let's say, is even. And I'm going to say, in this case, number. And all that I'm going to do simply is do the work we did earlier. So return the number mod 2 is equal to 0. But likewise, what I'm going to do here is simply put that little comment here that says is even called, let's say, called for with, and I'm going to simply say number. But notice this time, though, is even was called for 5 and 4, but it never ever got called for values like 6, 7, 8, and so on. Obviously, because those values are not going to be evaluated the minute it hits the result for 4. And you can see this go further on. If you were to take this particular function and change it to, let's say, is greater than 3, And over here, I'm going to simply say public. Let's say in this case, a Boolean again is greater than 3. And I'll do the same thing as I did for the previous one. So number is greater than 3, but I'm going to put that little message here so we can actually see it. So I'm going to say is greater than 3 and run the code again. You will notice that that was called for 1, 2, 3, 5, and 4. Again, it never touched for 6 and later. So you can also see the sequence in which this is evaluating. Every function is evaluated only on demand and only to the least number of times it needs to be evaluated. A completely eager evaluation would have done all the work, evaluated the is greater than 3 for all the 10 values. That would have been a waste already because 10 obviously is greater than the number of times this is actually evaluating to get the final result. But here comes the real charm. The functions like filter and map and so on, they all are lazy functions. So in other words, they're all intermediate functions. Those do not evaluate their Lambda expression until a terminal method is eventually called, and so they completely postpone it. So to see this very clearly, let's change this a little bit. I'm going to go back to this code and remove that part for a minute, and then I'm going to simply evaluate this, but I'm not going to print the result at this point. And in this case, of course, I'm going to say done and print the result of that and the done. So you can see all those methods were evaluated. Finally, it is saying done. Of course, if this was Haskell, it would have been a little bit more smarter to say you never use the result of that and you would have bypassed it, but not so in the case of Java. We called a terminal function that triggers the evaluation. However, what is going to happen if I were to stop right there at the end of map and I do not call the find first method at all? Well, notice what's happening in this case. We went to the stream, we called a series of intermediate functions, and what do the intermediate functions do? They say, I'll come back and evaluate it later, I don't have to do it now, but you never ever call the terminal method, and the lazy methods sit around and say, cool, we didn't have to do any real work. Well, this should be very familiar to you because I know there are some people at work like this, right? They come in the morning, they look around, and they ask you, where's the boss? You say, the boss is sick today, and they are all smile. They say, yes, I don't have to do any work today, right? That's kind of the laziness baked into it. I don't have to do any work right now because nobody is looking for the result. So if you notice, I run the code, all it did was print done, and it never printed those other messages. And the reason for that is none of those were actually evaluated, even though we passed them to this function. That's laziness baked into the stream already without us having to do much work at all. So what we need to do when we program with stream is A, remember that streams are lazy. And B, we have to know what methods are intermediate methods and what methods are terminal operations. That is something we have to very clearly know when we program, because if we try to program without knowing it, we're going to meet some really bad surprises in code, and it becomes really hard to work with it. So that's a common sense we have to develop when we program with streams in the case of Java 8. So using streams, we can start doing very nice lazy evaluations. And streams by default provide it. So there are two ways in which we can get laziness in the case of Java. One way to get laziness is to employ Lambda expressions in our code, and we can say, I'm going to pass a Lambda here, but I'm not going to evaluate it until a later time. And you saw me create the lazy class earlier, and you can use something like that to build your own laziness in your code. But the real easy way to do this in Java 8 is simply start using the Stream API, because the Stream API already provides laziness already very well, and so we don't have to do any extra work. It is something we can readily reach in and use it quite effectively. Well, that brings us to the next question. How do we go about really making use of this to build something a little bit bigger? Well, I did mention earlier that we need to keep track of purity of functions. That is something very important to keep in mind. So let me spend a few minutes on it. You cannot even imagine using lazy evaluation without purity of functions. And the reason for that is when a function is pure, it is not depending on any mutable variable, and it doesn't mutate any variable also. So in other words, when you have a function which is pure, as long as you send the input, as long as the input is exactly the same, the output will be exactly the same as it was before. And so purity of functions guarantees that the result will be consistent as long as the input is exactly the same, no matter how many times we call it. Now, why is purity so important for having laziness? Well, the reason is when a function is lazy, that function may be evaluated now, it may be evaluated later on, or it may not be evaluated at all. Well, if it is not evaluated at all, then if the function had a side effect, you're going to get a very different result depending on when it ran it and when it didn't run it, and you're going to be very confused, and the correctness is going to be messed up with. Well, if the function is going to run a little later and not now, it can be really problematic because the sequence of updates may be different every time you run it, and that's going to be buggy as well. But if a function is pure, meaning it doesn't have any side effects, then what it means is you don't even know if the function was evaluated until you looked at the final result. So the execution of the function is not relevant. The result that the function provides is what you really care about. Which means if the function was not evaluated, but you still got the result you really want, then that's great. There's no problem at all because you have the result, which is what matters to you, and everything that happened in between, the whispers, you don't hear them, and as a result, you don't care about it. So that's why it's extremely important for purity of functions if you ever plan to use lazy evaluation. If you don't have purity of functions, in other words, if your functions cause side effect, then absolutely you cannot use laziness at all because it will be extremely problematic. Here is one simple example to think about. Imagine a function is going to read from the user, and you decide that there are two functions, function 1 and function 2, both of them read from the user. What's going to happen if you decide to throw laziness on top of them? Well, in one run, that function may run and this may run later on, so the sequence of reading was 1 and 2, but in another run, it may actually turn around and this decides to be lazier than this one. Well, then you read second one and then the first one. Well, it doesn't make sense to do that in programs because the order in which you input data, after all, matters in programs, and you cannot arbitrarily change the ordering of the data. It'll mess up the result, especially if the operation is not associative. So purity is extremely important for that reason. Well, purity in functions opens the door for laziness, but laziness in turn opens the door for something even better, which is the ability to do infinite collections. So to look at one example of this, let's entertain this thought of a generator or a sequence generator, if you will. So let's say for a minute I'm interested in creating just a sequence of numbers and work with it. So what I can do here is, let me bring in the stream to begin with. So I'm going to say here is a stream.star, so stream.stream let's bring in. So I'm going to go ahead and say a stream, and we will call this as integer. So in this case, I'm going to go to the stream of integers and say dot iterate, and let's start with the 1, and given an element, give me the element, let's say +1. So if you look at this particular stream, this is an infinite series that you have on your hands. Very, very powerful, but yet very concise code, as you can see in this particular case. So what does this actually do? It says I'm going to start with a value of 1, but I'm not going to evaluate the values that follow until you actually ask for those values. And when you do ask for those values, it's going to only produce those values on demand when you ask for it. So in this particular example, at this point, how much work has been expended? And the answer is almost none. It didn't do any work at all at this point. So it's going to give us simply a stream on our hands. And so if you were to change this just a little bit, just to get the feel for it, let's go ahead and call this as increment, and I'm going to call E here. So this is going to become a int inc, which takes let's say, an integer number, and all that it's going to do is return number plus 1. And I'm going to simply go ahead and put a little statement here that says inc called, and keep in mind my statement again about not putting side effects, so don't do that in production. So notice in this particular case, I created a stream, and I'm going to assign it to actually a stream of integer, let's say. So integer, and I'll call it stream for a minute. Then I'm going to simply print that stream as a result and see what happens. Well, let's talk about what did not happen. Notice line number 7 never got evaluated. And the reason is we did not ask for the values at this time, and as a result, it never actually evaluated it. But let's say I'm not interested in all the values. I'm really interested in only even values, let's say. So what I can do now is I can go back to this guy and say, well, thanks for all the values, but I want to filter out only even values from this collection. And notice at this point, we got only the even values. Run the code one more time. It is still lazy because remember, filter is an intermediate operation. And as a result, it says, nah, I don't have to run this yet. I will run it if I really have to, right? So as a result, it postponed it as well. Well, guess what? I don't want all the even numbers. I want only, let's say, 5 even numbers. Well, I can say limit 5, and notice what this guy is doing. It says, my job is to make sure only 5 values pass through. You go to the limit and say, well, that's good limit. You're going to make sure only 5 values pass through, right? How many pass through? It says, I don't care, I'm lazy. I will do it when actually values begin to pass through. So limit is lazy as well. It doesn't do any work at this point. So it gets a little worrisome at this point. Is anything going to get done at all, isn't it? Well, of course it gets done when you eventually ask for a result from it. So if I say, for example, for each, and I'm going to say system.out, let's say print line, now it says, I better do some work because you are interested in printing the result right now. You called a terminal operation called for each. I better get my work done. So you can see inc was called that many times until it yielded 5 results for us. So without the print at this point, you can see the result only contains those 5 even numbers because we limited to the 5 values. However, notice in this case, if I were to stop right here at the end of limit and I do not run the last call, you can see in this particular case, nothing really was evaluated. So once again, if you notice in this case, if I say done, you can see that done was printed at the very end. But if I stop one step shy and at the limit, you can see it only said done. It never actually executed any of those. That's laziness built in already, as you can see. Extremely powerful concept baked in. So laziness makes it possible for us to write very highly powerful infinite streams. Now, what do infinite streams provide for us? It gives us a way for us to conceptualize problems where we don't have to worry about a bounded collection, but we can think of an unbounded collection. And it doesn't have to be a problem that only fits directly into collections. We can start thinking about other problems we normally work with, and we can see how we can formulate those problems into an infinite stream series, and absolutely we can do that as well. Gives us an enormous amount of power, as you can see, in ability to do this. That takes us to the next question, what about efficiency? Well, efficiency directly comes from the laziness of the evaluation, and as a result, you can see that we are able to get this benefit in case of not evaluating a function until you need it, and because you're postponing operations until you actually need it, you have the efficiency already. However, this brings up the question, how should we move forward when we start designing applications? Let's think about this for a minute. Suppose you had a list on your hand, and remember what's one difference between a list and a stream. A list is eager, it's concrete implementation. A stream is lazy. It doesn't do any work until it really has to do a work. Which means if you have a stream, you have a little, assumption on what potentially is going to happen, but you haven't done any work yet. So it's a work to be done, and only enough of that work will be done. That's basically what a stream gives you. So think about this for a minute. Suppose you are designing your libraries. What have you done until Java 7? You typically write your library functions where you return either a list or a set, and we normally pass list or a set to a function. The function does some work, and it returns back a list to us. It's really a good time for us to rethink about how we're going to develop these kinds of libraries. So let's take a look at one example of that to see how that's going to change moving forward. So to understand this, let's take one small problem and work with it. Let's say for a minute I have some stock info on my hand. Well, a stock info simply contains a ticker symbol, and it got a price for that particular stock. And I'm going to have a bunch of stock symbols that I'm going to work with. So I'm going to have tickers.symbols to begin with, and I got a bunch of ticker symbols. But what I really want to do is the following. Find the stock ticker whose, let's say find the first stock ticker whose price is greater than, let's say, $500. So I want to know which ticker symbol has a price greater than 500. So in order to perform this particular operation, I'm going to use a class called a stock fetcher. And if you look at the stock fetcher, let's see what the fetcher is going to do. It's got a fetch stock prices. And notice it takes a bunch of symbols as parameters, takes in a list, and what does it do? It imperatively goes through and gets one element at a time and gets the stock price for it, puts it into a stock object, and then populates the value. We don't have to worry about what's under this, but essentially it's creating a list and returning the list for us. Now, if you look at this code, immediately you should tell yourselves, oh my gosh, that's a eager evaluation. And what does eager evaluation mean? Eager evaluation means you don't care about efficiency. You really care to just get your work done, which eventually becomes more inefficient over time. But let's see what's the consequence of this in just a minute. So I'm going to go back to the code here. I'm going to create a timeIt.code so we can measure the time that this code is going to take. And what am I going to do here? We'll call it as compute eager, and I'm going to just call that function called compute eager. So let's go ahead and write that function called compute eager. And what am I going to do within this function? Well, first of all, I'm going to go to the stock fetcher, and in the stock fetcher, I'm going to call this method called fetch stock prices. And what does that take as a parameter? Well, tickers.symbols. So I'm going to just pass the symbols that we have on our hand. Well, you know what that's returning? It's returning a list of stock info. We'll call it stocks equals. Now that we have all the stocks, what's the next thing we do? We obviously want to select the first stock, which is greater than 500. So I'm going to say stock info, and we will say, let's call it picked equals. Well, we'll start with a null to begin with. Then I can say for stock info, we'll call it stock. And this comes, of course, from stocks. And what are we going to do within this? Well, we're going to simply say if the stock dot, let's say, price is greater than, in this case, 500, I want to simply say picked is equal to the stock, and then, of course, break out of it. And when we are done with it, we will simply print out the picked. So that is a very simple example of a code we have written. But there are a couple of problems already in this code. The very first problem in this code is, you can see that we actually did looping twice. One loop we did inside the function called fetch stock price, and the other loop we did outside, so we had to loop twice. Well, depending on the stock price, your loop may end early, it may end late, but you had to do the looping twice. But more important, you did a lot more work than you actually have to do. So the moral of the story is, yes, we have been returning list in the past. Yes, we have been passing list in the past. It's time for us to rethink about it. So let's go ahead and change this to compute lazy, but before that, keep in mind, the code took about 3+ seconds to run, if you recollect, 3.35 seconds to run. And of course, it says Google is the stock price. I'm going to change it to compute lazy. Now, what am I going to do with the compute lazy? Well, the very first thing here is, let's go ahead and say here is our compute lazy. And before we go further, let's get back to our stock fetcher. In this case, I'm going to create a static, and I'm going to say fetch stock prices. But notice this time, I'm going to say lazy. That's basically what I'm going to call a lazy implementation of this. What am I going to pass to this particular function? Well, I'm going to say stream of string symbols. So I'm going to pass in a stream rather than a list at this point. So of course, I've got to bring in a stream.stream at this point. So we will bring in the stream. Great. Now what do? I'm going to return from here a stream of stock info rather than returning a list itself. So the simple change we made here is, rather than receiving a list, we are receiving a stream. Rather than returning a list, we are returning a stream. So in other words, we are saying, sit back, relax, be lazy, don't do the work until you really have to do. So you're simply postponing the evaluation until a later time. So what does that do for us now? Let's go ahead and write this code now that we are here. So we have symbols on our hand. I'm going to say take each of the symbols, perform a map operation where I'm going to say stock util, and I'm going to simply call the get price on it and simply return that result. Notice not only we made the code lazy, we had to write a lot less code to make it lazy, right? So that was much more easier to write than the code we wrote in the beginning. All we had to do was simply say, do a map operation, return the result, I'm done, and that's what this code is doing. But of course, how much work did it actually do? And the answer is it didn't do a squat, right? It didn't do any work at all at this point. It says, I'll come back and do it later if I really have to. Well, that's our stock fetch stock price lazy with just the one line of code that's performing the mapping of given stock symbols to stock info. Now let's get back to this compute lazy. Well, I'm going to simply say over here, stock fetcher dot fetch stock price lazy, and I'm going to say tickers dot symbols dot stream. So we got the stream passed into this. Then I'm going to say filter, and given a stock info, give me a stock info dot price is greater than 500, and we did a filter operation on this guy. So this says, I know you got all the stock prices, but I want you to only give me the stock prices which are greater than 500. Then I'm going to say find the first, because I'm interested only in the first value that's available within this, and we are asking for the very first value to be provided. And then of course, once we get that value, all I'm going to do is simply print it out. So let's go ahead and output the result of that right here. So you can see in this particular case, we have obtained the result and printing the very first result that we get out of this. So when I run this little code now, you can see that in this particular case, it did take slightly less time. Looks like the internet connection actually here is fairly good. So it came back relatively quickly in the other case as well. But nevertheless, it did take a lot less time. And the reason, of course, is it is getting us the very first result. But more important, the question is, what is the amount of work it actually did? So to see this, if you go back to this code, just as an example, let's go to stock util for a minute. And in the stock util, here is the get price. I'm going to simply say get price for, and let's put the ticker right here, and go back and try to run this code. Well, in this case, let's go ahead and run this code in the other mode. Let's do the compute eager for a minute. And you will notice in this case, in the compute eager, it is going to evaluate the stock price for every single one of them. And because it's eager, it's going to get you all the values and then say what do you want to do with it. So you can see that all the stock prices was evaluated. But if you really think about this, what is this code doing so wrong? This code is completely ignoring what you're going to do with the result, and it only cares about getting you the collection. This code is very smart. It says, I'm not going to do any work on this until I get to know what you are going to do with the stream I return. This is very, very practical, isn't it? It's kind of like this. You're sitting and working at your desk, and somebody comes to you and says, what are you doing at 5 p.m.? Well, your usual answer is going to be, what do you want, right? If your better half, if a friend asks you, you would say, I don't care what I have, I'll come and hang around with you. If the boss asks you the question, you say, I got a lot of stuff to do, right? So the point is, you want to know what the implication is before you answer your question. It doesn't matter what you have at 5 p.m. to do. I want to know what you have in mind, and my answer will depend on who is asking and what they want to do. And that's exactly what this code in the bottom says. I'm not going to do my work until I figure out what you're going to do with the result I'm going to create. So it's extremely practical in that regard. So as a result, if you go back to this code now, and in this particular case, if you call lazy over here and evaluate this, you can see in this particular case, it only does less work until it could find Google, for example, and return the price. You can see that actually work very effectively. In fact, let's go ahead and say really a sad $5 for a minute and see what this is going to do. You can see it stopped at AMD and HPQ, so that only evaluated 2 values, whereas this guy you can see is going to still go on and evaluate a lot of stuff. If I change this to eager, that is. So this is going to be eager, and eager is going to do a lot more work than the lazy is going to do, as you can see in this particular case. So here is the lazy code, and you will notice that the eager is going to do all the work only to get to the initial value. There you go. On the other hand, you can see that the lazy is going to do only 2 values because it realizes you really don't need those values. So that shows you an example of how you can be lazy, and laziness can contribute to greater efficiency in code. You can see this one even shines a lot better. The 3.1 seconds versus a 0.4 seconds to compute, because this had a lot less work to do. So in the worst case, both the code would have the same performance. But in an average to best case, the lazy code is going to have a better performance compared to the non-lazy code. So to summarize what we talked about, the idea behind this is you really don't want to do a lot of work really fast. Your benefit is in doing as less work as possible to produce the result. In a way, in life, I don't believe in working hard. I believe in working efficiently. And it doesn't matter, right? If somebody comes to you and says, you know how many days I spent on this task? Sometimes you say, I don't care, did you produce the result? If you don't have the result, none of that really matters at the point, unfortunately. So efficiency is more better than hard work in life, and this is kind of the same thing. You want really efficiency. The laziness, along with function composition, really are baked into functional programming. And while functional programming emphasizes purity and immutability, those really are very important, not because they are fashionable. They are very important because we can do laziness with them, and with laziness we can do infinite streams, we can get efficiency in code. We saw some of those examples. And if you look at the reactive programming, that's what really excites me, because what is reactive programming? Reactive programming starts exactly where this leaves us off. It says, I'm going to program with streams of data. Well, what is a stream of data? A stream of data is a steady flowing data. You can never process a steady flow of data eagerly. You have to process them lazily. So reactive programming really steps in and takes the laziness to the next level with streams of data. And that's why programming with laziness is something we can quite benefit significantly. It is, of course, something we have to take time to learn, because it's not something we are used to in imperative style of programming. But as we are transitioning to functional style of programming, This gives us a nice way for us to benefit from some of these features. And as we get more comfortable, as we start writing more and more pure functions, we can greatly benefit from this. So be very eager to learn about lazy evaluation. I hope you found that useful. Thank you.